say thanks to organizers for inviting me to this program. It was a wonderful time, and for giving me a chance to give this talk. Thanks. Thanks, Tom and Ilya. This is a topic so consider standard Anderson model. I will consider here in these notations all the time it will be Z2, though the most of the statements are valid for higher dimension. And it's more, you can hear me? So. Sure. So, you say to raise my volume. Okay. So we assume usual conditions on dp, no? The main? Yeah, sure. Standard conditions on the distributions that there is density for the distribution of the potential in a site. There IID.
The dimension is?
Let's talk about 2, though I say that it's also true. So here is the main object, which is the logarithm of the determinant of the characteristic determinant in the box, or any number. Here is a theorem, which is the main result. So,
you go back to the previous.
Sure.
That's the U.
That is the U. That is right. That's right. So take this object, and here are the findings. Take a quasi one-dimensional box, meaning that the width is a little bit smaller than the length. Then it's possible to claim that the average of this function grows like beta naught times n.
The average of the log of the determinant.
That is right. I don't have time to stop here and to discuss some dispute between some experts on this subject, on localizations, that here it should be probably volume, which is probably true for most of E's, but I'm not sure that it's true for all E's. But this is a separate thing, and I don't want to waste any time for that, because there's a lot of stuff which I would like to discuss, and especially some recent simple applications of the method developed for that.
Beta naught doesn't depend on E.
Well, that is true. The bigger is E, it's better. I mean, there's no problem. Okay. Now, is it?
I going too fast here.
Yep.
I just want to understand what the first line. I guess I understood. Now I didn't get the second. Tell us
Second
about the
line.
part.
Second line addresses just the square.
Oh, square.
Just the square. Yes.
Square.
It's possible. It's possible to boost the result up to the square. So width and length are the same, but there's a price to pay. That means that here we have a little bit less than what we here.
I mean, what's the tau that you have
Any.
on the first? In the first
Oh,
one?
any.
Oh, any tau. Okay. So you
It's
want
just you just got to get through the threshold,
okay. So you want to be a
and
little
then
bit,
it's okay. This thing allows you to get through the threshold, and then it goes. You have to start beating the boundary condition. I will have a chance to talk about that, I believe. Now, so here it is a little bit less good, and there is quite a bit of work to go from here to here, because this is to beat this small tau, it's not so easy, but it's possible. So I won't talk about this result at all today. As a corollary, this implies the following effective estimate for the growth of the transfer matrices for this model. Namely, it's like that. This is an estimate for the upper Lyapunov exponent for this thing, which looks like that with the same constant beta naught. The conjecture is, the main conjecture, sure,
Go back just,
please.
so the beta naught is I guess, and maybe just.
Beta naught is the same
all
as,
passes you got
the
for-
beta naught is the same as was.
Okay.
Yep. So here is a growth which is guaranteed, effectively, etc. So there is an expression actually for this thing, but it doesn't matter. Sure.
What's the size of the lambda 0 in the previous slide? Is it for both sides? Both sizes, sorry. Both sizes that you had in the theorem?
No, no.
Lambda is superscript 0. Is it 1 kd or is it 1 n? Or it's, okay, it's in the first case.
Now here is a conjecture, which is a beautiful conjecture from which mathematical physicists, experts in this field, predict that actually the green function decays like that, meaning that the lower Lyapunov exponent is like that. It's a conjecture. I won't talk about anything. I won't talk anything about that. Now I'm heading immediately into the core of the method. The method consists of a combination of two basic things. First thing is related to the growth of the variance of this function. It turns out that this function always grows on average proportionally to the area or to the volume in the high dimension case. Furthermore, there is a sharp large deviation theorem for the values of this function, for the fluctuations of the values of this function from its average. Very sharp. Both facts are needed in order to get back and to prove this thing. Both are needed. So I'm going again to this line. Nothing is claimed here. This might be small number. Regardless of that, the claim is this, and this is true. This is just something which addresses the case of squares. Again, I won't have a chance to talk about that. And that is the first component. The second component consists of some a priori lower bound for the same function u. It cannot take too small values, the values which are too small. Namely, I'll jump a little bit. Thanks to technology, it's possible easily. This is a goal. To show that the negative deviations of this function, the deviations downstairs, go with very, very, very low probability. Meaning that here, etas which are good are etas which we are interested in. You have think of them as exponentially large, exponentially small in n. These are deviations. Why is that? Well, here is the logic. The idea of the method is as follows. On one hand, the function has fluctuations like square root, at least like square root of z. Right? There may be positive and they might be negative fluctuations. However, and the fluctuations will be of the magnitude square root of k times n, which is more or less n. Right? On the other hand, this estimate would say us that the deviations, even sub-exponentially small in the volume, like e degree minus n k degree epsilon, occur with very low probability. So what is the conclusion? The conclusion, how it can happen? The conclusion is that the average must be large. Do you understand this argument? I mean, this is the main idea, is that on one hand we have large fluctuations. On the other hand, fluctuations below the positive values are very rare. So most of the time, it must be. Of course, there should be some abstract lemma which explains this, what we got to know about abstract random variable, to say that if the fluctuations, the variance is big like z, the negative values are rare like z, the fluctuations are governed by large deviation, sharp large deviation theorem, then the average must be big like z. And we will come to this point, but before we do, I got to introduce another component of this derivation, which is responsible for this lower bound estimate. To introduce this component, I will need the following notion, so-called mixed Dirichlet Neumann boundary conditions. So we should think of that as we take a rectangle and we twiggle a little bit on the boundary. Look, you see? So we take arbitrary subset on the left edge, and we just remove it from the set.
Could you draw a picture?
Sure. So this is lambda. So twiggle a little bit its boundary, meaning that let's break it here, go here, one step in, then one step down, then go few steps down, then go back, then go again in, then we have a lambda gamma with Dirichlet boundary conditions.
Where's the Dirichlet, where's the Neumann?
Yes, if we put here like that, it's Dirichlet. If we put like that, it's Neumann, meaning that we go in and go all the way down, it's Neumann. And this is a mix of them. We will need also a reflection of this thing, which is, it's a good idea that I already have this picture on the blackboard, which is a reflected trajectory, meaning that it will go that way. So where here is red, here is white. And where here is white, here is red. So this is gamma, let's say prime, and this is gamma double prime. They are conjugated in this way. So to each curve like that on the left, associate this curve on the right. Clear? No? No. No. I introduce one-to-one correspondence between curves here and curves here. And the correspondence is as follows. Where here is white, here is red, and where here is white, here is red. This is obviously
White means inside.
in, out.
In, out.
Right? Good. That's right. It turns out that there is the following algebraic identity. That there are some constants which grow only polynomially in the volume, such that if you multiply this constant times characteristic determinant for the mixed condition with this gamma prime, and times characteristic polynomial with this gamma double prime, and you add them up, it's 1. For any v, this is a deterministic result. It holds for any v.
What is gamma t? With
This is exactly the set of points where you break. Or the same thing is to say, add up over all gamma prime with gamma double prime going accordingly to this one-to-one correspondence, which I just described. So, and what is good in that for us? Well, one thing is for sure good, that at least one term must be bigger than 1 over the total number of terms which we have here.
so this constant do not depend on lambda. They
They
not
do.
Depend.
I mean, there is an upper bound for them. They don't grow too fast. They don't grow exponentially. That is the main enemy. But they don't. So this is 1. And therefore, this maximum is at least like that. Well, why this is 2 minus k, not 4 minus k? 4 minus k. Well, here we have how many options we have here. Actually, no, 2 minus k. Everything is good. So, what is the meaning?
In general, these constants are complex.
For real e?
No, for complexity.
No. Constants, they are constants. Even for as
Oh, they don't depend on.
no. Even for the Greenland
Then it should be easy
whales,
to prove.
they are constants.
Then it should be easy to prove.
Of course, it's easy to prove. No one says that it's hard to prove. I didn't say. Well, just be patient. Before I do that, I want to give some cherry from the top of the pie, which is the next thing. So you have that. So what is good news? The good news that you have some kind of Wagner estimate for deterministic potential. That you can always twiggle a little bit the boundary to get off the spectrum. Right? For any deterministic potential. Oddly enough, it took quite a bit of time. The result was known for me for several years. I mean, I tried to work
What
other.
do you mean by Wagner estimate
Just a
of
sec.
deterministic potential?
You will see it. You will see it in a moment. You will see it. Just it will be just distance. Distance will be evaluated. No, no, quantitatively. It will be quantitatively. We are so far from the spectrum, at least. So, oddly enough, though I knew this result quite a long time ago, and I told it to Jean Bourgain that from that many things follow, I didn't realize that it has some consequences to Wagner estimate. Thanks to, I don't see him here, Shmuel Fishman, who asked me some tough questions, some tough mathematical questions, which led one after another to something which I call now robustness of the Wagner estimate. So this thing, this, as I say, deterministic Wagner estimate has consequence which is applied to Wagner estimate for random case. So, what is the deal? Wagner estimate says that if you take Anderson model, right, in any domain, and you ask what is the probability for E to be at certain distance to the spectrum, then it is no bigger than this distance times volume or area, right, and times the maximum of the density of the distribution in the side, right? Now, the proof, all proofs which are known as far as I'm concerned, rely on the fact that at each side of the set you have independent potential. You have to vary all of them. The question is how much this thing is robust. How much of the potential we can determine and just freeze them and put it whatever we want to say that Wagner is okay. Well, here is the answer, which is, I'm not saying that it is optimal. Moreover, since it's very, very recent result, I even can't say what is the right direction to go for, because it suggests quite a program, as you will see now. Look, take arbitrary subset of this set and assume that it has some combinatorial topological structure, which is as follows. Assume that you can cover this set with these rectangles. The number of rectangles in the cover doesn't matter at all. What does matter is the size of the cover and the fact that these are truly disconnected components of the set lambda prime. So they are, as you can see, the distance between these pieces I demanded 4 might be a little bit less. It's also good enough, but it's just to be completely. But you can imagine that this set can be huge. It can occupy almost quarter of the, almost 16 of the 4 and 4 in 2 dimensions, almost 16 portions, 1/16 of the whole lambda, right? So it's quite a bit, right? Freeze potential in all these points, whatever you want. And then you have Wagner. Of course, there is a price to pay for. What is the price? Well, the main thing here is that as long as this thing is sub-logarithmic in lambda, it's not dangerous because it pops up in the exponent. So most of things where we use Wagner go to sub-exponential estimates. You need something sub-exponentially. You got to avoid the spectrum to be sub-exponentially close to E, right? It's always, almost always enough. It's, of course, it's something not exactly correct, but still. So as long as this, let's say, square root of log of modulus of lambda, no matter how many you have, the only correction factor for Wagner would be this exponent. So if you will write down here negative power of that, so you will have exponent 8 blah blah blah, right? So as long as epsilon is a little bit smaller, it doesn't feel at all what's happening. So what is the relation between these, as I call it, deterministic Wagner?
Yeah,
Is this your way of controlling the degree of the polynomial?
Which polynomial?
Interacting sum.
Hmm?
Controlling the number of zeros.
Well, of course, yeah, but it doesn't go that way. No, just a second. We will see. It's easy. The way from, I'm
Before
sorry.
you go to the proof, I want to understand the statement. I haven't understood the statement.
No, of course. Let's chew on it. So here is the statement, right? This is a just a second. Give me a chance to finish, please. So this is the deterministic. This is a deterministic Wagner estimate, right?
I don't know, because I haven't understood it yet. I don't understand the statement yet.
Maximum, you can twiggle the boundary so that you get off the hook, right?
Regardless of what the V's are.
Regardless, but of course, the set will depend on V, of course.
What's that?
This boundary will depend on V, of course. I mean, for each V you have,
We fix the potential, and then we have a right deformation.
Okay.
you give me V, I give you gamma, right?
Of any V, there exists such gamma that as
Right, that's right. That is what explicitly
But you're only
written.
varying the V's through the boundaries, what you're really doing.
That's right.
Or
That's
I
right.
might-
But that is irrelevant in the derivation, which is going to be for the next.
I can have V equal to 0. Do I understand that correct?
Excuse me?
I can have V equal to 0.
Yes, that's true. Whatever you want. Now, let's go back to this thing. So we have this kind of set with this topology, combinatoric set topology. The good news is that you can have as many points as you wish. The main parameter is the size of this smaller square, right? And then you build this quantity, you build this, so you take the maximum size of this thing, and you take exponents. This is something that it's a technicality. I assume that it is distributed, that the potential is distributed, let's say, from -1 to 1, something like that. That you can forget about B naught. For other potentials, it will be a little bit more delicate, but I don't want to discuss these things.
But this epsilon lambda is exponentially small, do I understand?
It's exponentially small in this volume. Therefore, as long as this area or volume is sublogarithmic in lambda, as long as these pieces are sublogarithmic in the size of lambda, it's not dangerous, because the only applications of Wagner are addressed to the case when epsilon is sub-exponential in size, right? So this is harmless as long as this is not let's put it that way, as long as this is small, relatively small. But how many doesn't matter.
How many what?
How many pieces you have. The main thing is that you don't have something contiguous, which goes like that, one close to another. That is a problem. Okay?
jump.
Hmm?
Jump back.
Oops. Sorry. I was keeping it pushed. Pressed, to be accurate. So this is the statement, and now I'm going to say to you that actually the derivation of this from Z is very easy. Very easy. Here it is. So now, here is the form of deterministic Wagner estimate which you asked for, right? So given a box, you can twiggle it on the left or on the right. It's up to you. So that the norm of this operator is no bigger than Z, meaning that the distance to the spectrum is not bigger than the reciprocal of Z. Are we clear? Yep? No? Well, this is a claim. I'm not saying that it's automatic. Just a second. It's a few lines derivation. But let's first digest the statement. Whatever is V, you can always twiggle either left edge if you wish or right edge as you wish. It's up to you. This is done because some of these sets can sit exactly at the edge, right? And then you cannot twiggle this edge. Then you have to twiggle this one, right? So to avoid such unpleasant situation, you have to have some freedom. You have to have a chance to wiggle any of the edges, right? That's what is claimed here. Okay? So that. Of course, you will say, why is that? Well, actually, it's elementary.
Oh, is it you have a P? I forgot what the constant V0 is.
This is the size of the interval on which rho node is supported. You can think that it's 1. And this is volume.
Yes.
Therefore, volume appears. But this is the volume of a small thing. Just a second. Don't be so fast. Just a second.
Where is the small thing?
This will be applied to these small guys, not to the big guy. This is going to be applied to small boxes, not to big boxes.
K and N refer to the big box.
Yes, but it's for any box. Who told you that these are K and N which are under the question? It's for anyone, right?
Yes, but lambda and lambda prime are also big boxes.
They are as big as this box is. Not
Yes.
big. So they are sub-boxes of this small box.
Deformations of lambda.
Deformations of lambda. Yes.
Yeah, I probably should go here with N small and K small.
Yeah, just different notations.
Different notations, but I hope it's clear enough that it applies to any box. There is no any limitation. Any box. It's a general statement. So, why is this true? How to go from the estimate of the determinant to the estimate of the norm of the inverse, meaning to the estimates of the minimum of the eigenvalues? Well, easy. The upper bound for the eigenvalues is known. The determinant is a product. So if it is bigger than something, that the smallest one cannot beat everything. It cannot. It's just out of question. Right? So going back to this claim, this is exactly the deterministic Wagner estimate. Right? Now, how to go from the deterministic Wagner estimate, from the deterministic Wagner estimate to the robust Wagner? Well, let's read the previous statement, this one. Let's apply it to each small box. Since the boxes are disconnected, the norm of the direct sum, inverse is just maximum. So we arrive at the following claim. Whatever is lambda 1, there exists a lambda prime, right? Which covers, there exists lambda 1, which covers this lambda prime. So you cover everything with these boxes, and then you apply. So there is lambda 1 such that the norm of this is no bigger than exactly this. This is just a calculation, how big you have here. The epsilon is taken deliberately much smaller in order to save a little bit. You understand what I mean? Why do we need to save? Well, because of course nothing is going on here without sure. Almost in each talk it was. If you have arbitrary matrix, H is invertible, then sure says that take this complementary operator, build this one, and this will be inverse to this box, to this operator. And the norm is no bigger than the norm, than twice the norm, the maximum norm of this. So that is right. Now, going back here, we have that lambda naught is not empty, so we have at least one potential not frozen, and that is it. Is it clear? Look, once again. Given this set, we can build something so that this is correct. So we can twiggle around it, the boundaries, to make that. Then we use sure, so we turn it out on the complement, as usual in sure. And since we still have here at least one potential free, this is enough, we are okay. Correct? But this is just an application of this thing, of course. I'm not, as this is not the main goal, and this is something recent, as I said, and the main goal was, of course, theorem 1, which is that is the main goal. But this is just some byproduct. So here is something which I told that it is needed to understand. Some general statement which says that what you got to know about some variable, abstract variable, to make the following conclusion. If the variance is large, if you can bound it that way, if the deviation to the negative part are very, very rare, if the large deviations from the, oops, I missed here the average, sorry, xi minus xi average, this is large central limits or large deviations, are also, there is no need for such sharp, but for sharp estimate here, what is needed sharp estimate here, the deviations are typically of the magnitude square as the fluctuations. So if you have all that, and on top of that you know that this is large enough, so it dominates everything which you cook up when you go through the analysis, then the conclusion, oops, here it is also average. Sorry, twice. Okay? So this is the main drive. If you can prove that something has a big variance, the chances of it going down are small. The deviations go like in central limit theorem, then its average must be at least as big as the deviations, or a square root of. Now, few words about the. I have absolutely no chance to talk about why the variance of the logarithm grows proportionally to volume. But one thing which
Misha, this previous statement about random variables, right? Can you draw a picture? Because
we can talk about that. This is something which is you just trust me on that. This is for student, which is
exactly.
yes
exactly.
for student. And
Yes,
that's
exactly.
yes.
But we are
So
not.
yes, but we are not students. We are instructors. So we have to to go through that in order to explain to students, right? No, it's a joke, but trust me on that this is okay, okay? Not that is the heart of the matter. I won't have a chance also to go to the heart of the matter in regards of the fluctuations, which is the hardest part of the work. But this algebraic part, which is related to some lower bound, to some deterministic Wagner, is of course everyone. I believe everyone would like to see what it should be easy, right? As Yuri Mikhailovich, Yura, I don't know how to say that. Yes, said it should be easy. Of course, everyone has intuition because it should be something algebraic plus a little bit of analytic functions. You have two polynomials. You have two functions, two polynomials. You know the relation between the roots, and one polynomial you know its degree. Another one you don't know its degree, but you have some information about that. One polynomial is clear because it is just it's just characteristic polynomial. It's monic polynomial in E, etc. Another one might have some cancellation, so you have to work a little bit to be a little bit careful with that. But still, and that is the reason, by the way, that these constants appear. You see, just to compensate anything which could happen here. But everything, of course, goes to transfer matrices. And what is good that the idea applies in many dimensions also. It doesn't matter. In all these things, transfer matrix is good enough to make an intelligent conclusion about the deviations from the spectrum, about this deterministic Wagner estimate, which is good news. The idea is as follows, that if you go with the transfer matrices, then you have this is a usual formalism. It's of course symplectic, therefore its determinant is 1. On the other hand, so it's 2k times 2k matrix, which splits into 4 blocks, which are absolutely natural and correspond to Dirichlet and Neumann conditions. This determinant, the determinant of Z, is identically equal to the characteristic determinant of the Dirichlet conditions.
It's baffling. Why you need Neumann-Dirichlet conditions?
Yeah, but what? Yeah, okay. Let's go a different way. The only way to get away from the spectrum is twiggle the boundary, right? Or twiggle something inside. Doesn't matter, right? The boundary seems to be very convenient because if you go to the transfer matrix formalism, then you have something at the beginning and something at the edge, and you want to twiggle it a little bit, and then of course you are better off, right? Well, I'm not saying that this is a proof. I mean, I have a preprint, I can give it to you. So here's the claim. So here, the constant is just 1. For this particular one, it is 1. But once you mess up with these guys, you end up with some minors which are constructed from these first k rows and some arbitrary chosen k columns. And a priori, for a general potential, there might be cancellations. Why not? Why the degree cannot cancel out? Do you understand what I mean? So there is some description, blah, blah, blah. There are important relations between these 4 matrices. how they are not, they have a canonical relation, how to get one from another by going one step back or one step forward. So there is this thing, basic relations between them, which helps a lot. Then what we do, we just take the expansion, we take, Laplace expansion along first k rows, we add them up, and we end up at that. And that is it. Determinant is 1 because it's no, because it is symplectic. So I'll better stop here, and given that there is only 5 minutes left, and anyways I won't have a chance to progress much, I would like also to thank again the organizers. Thank you very much. It was very good time.
Questions, please? Yes, please. Could you come back to the slide where you described the configuration of exceptional statements?
Yeah,
You
sure.
can freeze the random variables. Okay, my question is, what's the minimal number of random variables that you need to wiggle to get the regular estimate? How many do you need? A single one. So you.
No, look here. Here is
I
answer.
see a pseudo-empty sign, right? This I see.
One is enough.
Okay. So
What
one
is
enough.
what would be interesting? Let me just take this opportunity, because I think that it suggests some kind of a program to study. You see, you can allow some big pieces, but what you can't allow, something like just dissection of that. This is too big, right?
But you don't want the pieces to be big, right? The lambda primes, you want them to be small, because if
Well,
lambda prime gets big.
I wanted to be any.
No, but-
To be honest, yesterday I claimed that I can prove it for any, but Victor immediately got me.
but-
So the more you can freeze, the better, because the more you can freeze, the more robust is Wagner. This thing says that if it is not something connected, then you cannot destroy Wagner. That is my answer. There is disconnection. You see, this is crucial. Excuse me?
Maybe this was my question.
That is exactly.
No, what I'm asking, okay, I understand, but if I understood well, the important thing is that the individual pieces lambda prime of J need to be small.
In this statement, yes.
And you need them to be small.
Yes, but I'm not. But take into account that that might be not the optimal way to argue. Maybe some rescalings, etc., can improve quite a bit this thing.
Many
Yeah.
things can improve the thing, I'm pretty sure, but.
Okay, let's put it that way. The fact is on the
So
plan.
what you are saying, if you have such a decomposition and there is a single random variable that is left over, this is enough to
This
get
is-
Wagner. As long as the lambda j's, for example, are bounded by their size is bounded by a fixed constant, right?
Constant, on even if it is sub-logarithmic, it's
Let's
also
take a
cool.
constant. Let's take a constant. Right? So, okay, just to. get
Good.
the picture.
Yeah.
It seems that actually you need alive all the potential values outside the patches, and you want that they
Just be
still-
careful. Be careful. You see, I made it already bigger, slightly left, and that is enough. And if I subtract those, and I still something, let's be careful. Okay. No flow.
No, I'm saying that all which is outside this slightly bigger patches should be alive.
That's right. That's right. Of course. But the question was, how many you need outside? If some one of them not alive, you just count them in lambda prime, and that is it. I believe that's it.
Okay, do we have more questions? If not, let us